we are going to start off Unit 9 just by reviewing a couple things we already learned. We already learned about, the basic types of chemical bonds at the end of the last unit, right? We talked about ionic bonds, where you have a metal and a nonmetal, or you have a metal and a polyatomic, or a polyatomic and a nonmetal. And basically, it's where they give electrons. So the positive cation, it gives electrons to the negative anion. You guys remember that, right? And then they attract to form a compound. So that's an ionic bond. Today, we're going to talk more about covalence, but covalent bonds are where they share electrons between atoms, and it's going to be between two nonmetals. And the metallics are formed by electrons that move freely through a metal. This was at the end of the previous unit, so I'm not going to spend too much time on it, and you guys don't need to copy it down, but just kind of a refresher. Okay, so if you guys are good, let's take a second. I want you guys to draw the Lewis structures, the dot structures, not the shells, for sulfur, sulfur's MCI, and argon. Okay, so I'm going to do sulfur, and then I'll have you guys try the rest on your own. So for sulfur, sulfur is right here on the periodic table, and so Lewis structures are pretty easy. All you need to do is count the boxes as you go down the periodic table. So sulfur's in the third row, so that means we only draw the valence electrons on the outside shell. So there's 1, 2, 3, 4, 5, 6. Since sulfur is the sixth box, that means sulfur has 6 valence electrons. So sulfur is going to be S, 1, 2, 3, 4, 5, 6. And that's the Lewis structure for sulfur. Okay. So when you draw Lewis structures, all you're drawing are the valence electrons, the ones in the outside shell. Should be review. Any questions on that part? You guys showing? Okay, so I'll give you guys a minute. I want you guys to try doing sulfur's MCI and argon. All right, maybe another 30 seconds. All right, you guys ready to go? Okay, so sulfur's MCI, what's the charge on sulfur's most common ion? Anyone remember? Yeah, -2. So remember the columns, this is +1, +2, +3, no MCI, -3, and -2. So sulfur's MCI is -2. So we have S2 minus. Now, regular sulfur has 6 valence electrons, right? So if the charge is -2, how many valence electrons does S2 minus have? 8, yeah, because you have to add 2. So you just need to do S2 minus and draw 8 valence electrons around sulfur's MCI. So that's how you would do the Lewis structure for S2 minus. All right, Now we got argon, which is AR. So all we need to do is go on the periodic table and look at AR. So if we look at AR, it's at the very end. So how many valence electrons does AR have? 8. Yeah. So if you guys notice, argon's Lewis structure is pretty much the same as S2 minus's Lewis structure. Okay. So that's how you would draw the Lewis structure for those compounds or those atoms. All right. Any questions about any of the three? All righty. Okay. So right underneath, a couple things. Atoms, we already know that they gain, lose, or share electrons to stabilize themselves. That's why they form bonds, is to stabilize. And when they have complete shells, they look like the noble gas at the end of their row. So sulfur is in the third row. Argon is at the end of the third row. So they gain electrons so that they can look like the noble gas. Okay. Now this observation, we call that the octet rule. So just write that term down somewhere on your paper, just so that you guys have it handy. The octet rule. You're going to be hearing this term a lot, and it's kind of a good guideline for doing some of the things that we're going to be looking at this unit, the octet rule. Now, anyone know what this term octet means? 8. Yeah, 8. Oct, right? Like octopus, right? 8 legs. October is not the 8th month, but it starts with oct. Yeah, but anyway, oc. It is very strange. Okay, but we have the octet rule. So 8, which means that for atoms, they want to have 8 valence electrons on the outside. That's what the octet rule is. It just means that atoms, they tend to want 8 valence electrons. Interesting.
I just remember that.
Makes sense though, octet rule? It just means atoms are going to want to usually want to end up with 8. Okay. Yes.
What's an example if it doesn't follow octet?
Oh, we'll get to that. There's a section called exceptions.
Okay.
All right, so let's move on. So that's Lewis structures. We're going to talk about ionic bonds and what they look like. So we already know that ions are generally formed when metals, they give their electrons to non-metals. And then that causes the metal to become a cation, so positive, and the non-metal to be an anion. And then you got positive and negative, opposites attract, and that forms an ionic bond. And so what we're going to do is we're going to use Lewis symbols to represent some reactions. So I'll do the first one with you, and then I'll have you guys try the second one on your own, okay? So we have lithium and bromine. So I want you guys to take maybe 30 seconds. I want you to draw the Lewis structure for lithium and for bromine, okay? Lithium and bromine. Take about 30 seconds to draw the Lewis structures for those two. All right, let's do lithium and bromine, guys. So we have lithium. How many valence electrons does lithium have? Yeah, it's the first box. Okay, bromine is the one that you might have got a little confused on. So if we look at bromine, it's all the way here, right? So we're going to count to bromine, but we are going to count 1, 2. But if you guys remember, we skip this entire middle section, groups 3 through 12, the transition metals. So we go 1, 2, and then we skip all the way to group 13, 3, 4, 5, 6. And so bromine has 7 valence electrons, because remember, these are the d orbitals. It's one level underneath the shell 4. So that means we skip them when we do our Lewis structure. So bromine is going to have 7 valence electrons. Okay, make sure you guys didn't do 17. Okay. Okay, so we said that ionic bonds, that the metals give electrons to nonmetals. So if we want to show what happens between lithium and bromine, lithium is going to give 1 electron to bromine. Okay, because lithium wants to lose 1, and then bromine wants to gain 1, right? And so if lithium loses an electron, what's the charge on lithium now? Yeah, +1. So it becomes Li plus, okay, let me do it in a different color. Okay, so we have Li plus, and bromine gained an electron. So what's the charge on bromine now? Yeah, -1 because it gains 1 electron, right? Got something negative. So bromine becomes -1. And so we know that opposites attract. So lithium and bromine, they are going to attract, and then they form LiBr. And that's how they form an ionic compound. Okay? Make sense? And if you guys remember, this is the reasoning behind most common ions, and when we found ionic compounds, how they balance each other out, the positives and negatives. This is the reason behind all that. Okay. All right. So I'll give you guys maybe about a minute and a half to try the third one for calcium and oxygen. Okay. Show how those two react with one another. Calcium and oxygen. All righty, you guys ready to go? Hopefully not too bad. Okay, so let's look at calcium. How many valence electrons does calcium have? 2. Okay, so we're going to do 2 for calcium. And then how many valence electrons does oxygen have? Sorry, I can't hear. 6, thank you. 1, 2, 3, 4, 5, 6. And so we know that calcium is going to give 2 of them to oxygen. And then that's going to turn calcium into 2+, oxygen into 2-, and then that's how they form CaO, CaO. Okay. And then the same happens if there's multiple involved. So calcium, we know, wants to turn into 2+. If we had 2 bromines, we would have Ca and then 2 Brs, and then calcium will give 1 to this bromine and 1 to that one, and whatever combination that we want to make. Okay, so that's basically how ionic compounds are formed. Okay. Any questions on this? Yes.
Say you had like 2 different atoms that have the same amount of valence electrons. How would you do that?
Like sodium, lithium, and then like an oxygen or something. Yeah, so usually those don't form compounds because of reactivity. So like, because it's very rare for there to just be like one of an element, right? Usually there's going to be like multiple. So the more reactive one is going to react with the anion before the other one can. So like lithium and like potassium. Lithium is a bit more reactive. And so the 2 lithiums will take the anion before potassium can get in there. And only once the more reactive one is used up, then will the other one be used. Okay. Good question though. Okay, so a couple things to review about ionic compounds. Again, this is review from the last unit. Ionic compounds, they're usually brittle, which means they kind of break apart easy. They're very high melting points. I don't know if you guys ever tried this. Maybe you're not as dumb as me, but have you ever tried to like burn salt? Okay, yes. Yeah, salt on a frying pan, it's like, it doesn't melt at all, right? Like sugar melts really quickly, but salt does not melt unless you like throw it in the fire. And even then, it doesn't melt. So they have very high melting points. They form crystals, and they're easy to break apart. Like if you had a piece of salt and then like you hit it, like it cleaves pretty easily. And then they have a very well-defined 3D arrangement. And it's because of this, because the positive cations get surrounded by the negative anions. They form these lattice structures because they want a specific number of anions to react with, and so that's what forms their 3D crystal, like pretty well-defined arrangement. Now, ionic compounds, they're stable because of the attraction between the ions, and then they form something called the lattice. So this crystal structure right here, this 3D arrangement is called lattice. And so the measure of this stability is called lattice energy. Okay, so write that term down. That one's pretty important. Lattice energy just basically means how stable is the lattice? How stable is that 3D structure? How stable is that crystalline arrangement? Okay. So we can actually calculate that. Lattice energy basically just measures how much energy does it take to take 1 mole of a solid ionic compound and turn it into the gaseous ions, which is kind of weird to think about. But if you had 1 mole of salt, right, sodium chloride, how much energy would it take to break it into Na plus gas atoms and Cl minus gas ions? Okay, and then we have that right here. It's just a delta H. We're familiar with that term or that symbol. It's a delta H lattice, and it would be positive. So does that mean I have to put in energy or it releases energy? Yeah, you have to put in energy. And a lot of energy. Any questions on what lattice energy means? What it's measuring? It's basically how much energy does it take to turn your solid ionic compound into a gas? Yeah.
When I was doing the homework, it mentioned something about like the size. So does that mean like how big the lattice structure would be?
No,
like,
we'll get to that in just a second. It's down here with the equation. Yeah. Man, this is the problem of having you guys read before. You guys know stuff. No spoilers. I know. I know too much. Okay, so if you guys notice this, the energy, I mean, you guys might not be able to tell, but it's a lot of energy. Just think about it. Like melting salt is already really hard. So how much energy would it take to vaporize salt, right? That's how much energy it takes to reach the lattice, or that's how much the lattice energy is. And so here we have a chart with just some common ionic compounds and their lattice energies. Now, you don't need to memorize this. If anything, it's not, you probably won't see this on the test, but being able to manipulate the formula is very helpful. So this is the formula for lattice energy. Okay, so I'm going to break down this formula. Here we have K on the top. K is just a constant, and then lattice energy, Q1 and Q2 represents the 2 charges. So for example, if we had something with a +1 charge, and then we had something with like a -1 charge, that's what would go inside the Q's. And the D right here on the bottom, it just means distance. Okay, so the distance between the 2 charges. So the higher the distance, right? If we make the number on the bottom of a fraction bigger, the number gets smaller, and so it's inversely proportional. Okay, so here I kind of break it down for you. The bigger the ion charges, the greater the lattice energy, and the closer the ions are, the greater the lattice energy. Okay. And this equation we will be using at the very end of the year, right before the test. I think it's one of our last units. You don't need to memorize it. It's on your formula sheet, but just understand this equation. It's very helpful in chemistry, and if you take physics later, it's a big part of physics as well. Any questions about that before we move on to 9.4 question? All right, you guys cool to move on?
Yeah.
All righty. So in 9.4, it's asking us which one of these three substances, these chemicals, MgF2, CaF2, and ZrO2, which of these do you expect to have the greatest lattice energy? And we need to explain using the equation below. Now, this means we got to look at all three of these compounds. I'm going to do the first one with you guys, and then I'll have you guys do the second and third one, maybe with the partner, and then split it up, okay? So let's look at MgF2. Now, we need to use this equation right here. Now, K is a constant, so that means that it doesn't matter what compound we're looking at, we always use the same K value. So it doesn't matter what this number is. What does change are the Q1 and the Q2, and maybe the distance, but we'll talk about that later. So let's look at the Q1 and Q2. These are talking about the charges of the two charged particles. So here, ions. So if we look at MgF2, what is the charge that's in Mg? Yeah, +2, because it's balanced out by F2, right? And what's the MCI for each fluorine? Yeah, -1. Okay, so here we have our Q1 value and we have our Q2 value. Okay. So if we plug this into the equation, basically the lattice energy, the electrical energy between the charges would just be K times +2, -1. We don't know the distance, so let's not do anything with that for now. We'll just put D on the bottom. And if we simplify this equation, we would just have -2K D. Okay. So that's how you would calculate the electrical energy for MgF2 between the positive and negative charges. I'm going to actually rewrite that like this. I'm going to put the 2 on the outside just so that it makes it easier to compare later. Okay, so what I want you to do is work with someone next to you, unless you don't want to. But I want you to find the lattice energy for CaF2 and ZrO2. Split it up amongst yourselves. I'm only going to give you a minute to do this. And then after that, see if the three of you can figure, or the two of you can figure out which one of these has the greatest lattice energy, the highest lattice energy value. All right. You guys need a little bit more time, or are you guys ready to go over it? Okay. All right, let's go over it. So for CaF2, pretty similar. What's the MCI of calcium? Yeah, +2. So for Q1 for CaF2, Q1 is going to be +2. And what would Q2 be, the charge for F? Yeah, -1, same thing. So if we plug in the values into this equation, it's gonna look the exact same, right? So CaF2 is gonna have a lattice energy of -2K over D. So pretty similar. The D value is gonna be different just because of the shells, but we're not too interested in that right now, okay? Any questions on how we found CaF2? All right, let's go to ZrO2. Now, this one's a little bit more difficult because we don't have an MCI for Zr, right? Because it's in the middle of the periodic table. It's a transition element. So if we take a look at oxygen, we know the MCI for that. What's the MCI for oxygen? Yeah, -2. And there's 2 of them. So what does the charge on Zr have to be in order to balance out the oxygens? It needs to be 4. Okay, so already we're going to see that it's a little bit different than this, right? So if we use our equation, that means we'll have K on the top, we'll have +4, we'll have -2, and then we'll have D on the bottom. And then so if we solve it out, we'll have -8K over D. Okay, so if we take a look at these values, we have -2K over D and -8K over D. And so that means that ZrO2 is going to be the one with the greatest lattice energy, at least with the information that we have. Maybe the distance changes the values a little bit, but we don't have any information about that. So we're just going to have to go off of what we have. So ZrO2 has the greatest lattice energy. Okay, now you might be looking at the negatives and be like, wait, but that means -2 is bigger than -8, right? But the sign in this equation, we talked about it very briefly. A positive electrical energy means repulsion, they repel, and a negative electrical energy means that they attract. Okay, and so the more negative the number in this situation, the greater the lattice energy. Okay, so I wanted to go over that problem because on the AP test, a lot of times you're gonna have to manipulate equations like this without knowing all of the values for the variables. Sometimes you're gonna have to keep it just the letters, and so you do need to be comfortable doing math without knowing every single variable in the equation. Okay. Any questions about this problem? That's chilling. Any questions about ionic compounds in general? Because we're gonna be moving on from that now. That's a tired. Do you guys want to break now? No? Or a little later? A little later? Okay. Just want to gauge where you're at. Alrighty, let's move on to, we're going to skip 9.5. This one you can actually do on your own. It's a pretty easy problem. We're going to go straight to covalent bonding because this is going to be the important part for this unit and pretty much for the rest of AP Chem, understanding covalent bonding. It's more common than, at least in terms of problems, than ionic. So covalent compounds, they're formed by nonmetals when they share electrons with one another. So I'm going to zoom in a little bit here. But if we take a look at this equation on the left, we have the Lewis structures for 2 hydrogen atoms. And so hydrogen is going to want to complete the outside shell. So if you look at hydrogen, how many shells does regular hydrogen have? 1, right? So hydrogen has 1 shell. And what's the maximum number of electrons that can go inside of that first shell? Yeah, it can hold a maximum of 2 electrons, right? And so hydrogen only has 1. And so what hydrogen wants to do is to fill up that shell. Now, we learned before that one thing hydrogen can do is hydrogen can lose an electron, right? And become H+. You guys remember that? That's why the MCI is +1. However, hydrogen can also combine or share electrons with another atom, could be hydrogen or a different one, and they could share to have 2. They're sharing the ones in the middle. And they could form a covalent compound, and it could form H2. Okay, this is H2, hydrogen gas. So that's another option that hydrogen can take to fill up that shell. Okay, chlorine can do that as well. We have 2 chlorine atoms, and so the 2 chlorine atoms can share 1 electron with one another. and then it could fill up the shell and it can form Cl2. Okay, so that's what covalent compounds are. It's when these elements, they share electrons with one another in the valence shells so that they can kind of have a full shell, but they're sharing it with another element. Okay, yeah.
So if you were to ever like base the two circles off, how many?
So usually when we draw it, I'll show you guys how we're gonna draw it in just a second. We don't draw it like this with every single electron. We usually draw a line to represent that they're sharing electrons. Yeah, but we'll do that in 9.6 in just a second. Alrighty, so we're gonna do a couple of practice problems because learning how to draw these covalent compounds, it's pretty important skill for the rest of chemistry, and especially if you want to study chem more in the future, maybe organic chemistry, it's literally all just this. And so let's go to 9.6, okay? So here we're gonna determine the structure of NF3 using Lewis structures. Okay, and we're going to identify the bonding and lone pair. Now we'll talk about that in just a second, so don't worry too much about that. And so there are a couple rules that you want to follow when you guys are drawing Lewis structures, okay? The first thing you want to do is you want to organize your elements, but what you want to do is you want to put the more electronegative ones towards the middle. So you want to place the elements that are more electronegative, and you guys remember the pattern as you go up and to the right, it becomes more electronegative. You want to put the more electronegative ones towards the, I'm so sorry, not towards the middle, towards outside. Yeah, and it makes sense because electronegative means they're selfish with their electrons. They don't want to share them. And so they want to be towards the outside so they don't have to share, because the ones in the middle have to share, right? And so the ones towards the outsides don't. And so the more electronegative ones go towards the outside. Sorry about that, guys. All right. So if we take a look at this compound right here, we have NF3. Okay, which one is more electronegative, nitrogen or fluorine?
Fluorine.
Yeah, fluorine is more electronegative. So that means nitrogen is probably going to go in the middle, and then we're going to put the F towards the outside, okay? So we'll kind of, it doesn't really matter how you organize it. You can do it however you want. Just make sure nitrogen's in the middle and the fluorines are on the outside, okay? Okay, the next rule that you want to follow is you want to draw the valence electrons, okay? So draw valence electrons. Okay, which means that you're just going to go into your picture right here and you're going to draw the valence electrons. So we know that fluorine has 7. We know nitrogen has 5. So we're just going to draw the valence electrons for all of them. Can you guys see that okay? Or should I make them a little fatter? You guys can see it okay? Okay, and then the last rule that you want to know is that you want to create octets for all of them. So make sure everybody is going to have an octet. So you get an octet, you get an octet, everyone gets an octet. Okay, so let's take a look at it. So fluorine right here, it does not have an octet, right? Actually, none of them have octets, right? And so what we want to do is we want to organize them and have them share electrons so that every single one of these atoms have an octet. So how many more electrons does fluorine need to get an octet? Yeah, it needs 1 more. So I'll write 1 more. Okay, and that applies to all of the fluorines, right? Because they're the same element. And then how many electrons does nitrogen need in order to form an octet? Yeah, it needs 3. So it needs 3 more. And so what that means is this fluorine right here is going to share an electron with nitrogen like this. They're going to share these. And that way, let's say if I cover this nitrogen up, fluorine has 8, right? But then if I cover up the fluorine right here, nitrogen, it has 1 more. Okay? You guys see that? It's sharing the electrons. And now this fluorine is good. This fluorine has 8, so it's following octet. Nitrogen, not yet, but I mean, we got 2 other ones to work with. And so what's going to happen is this nitrogen is going to form an octet with, or share electrons with this fluorine. And this nitrogen is going to share electrons with this fluorine. And so every single fluorine now has 8. And nitrogen, if you cover up the fluorines, nitrogen also has 8. There's 1, 2, 3, 4, 5, 6, 7, 8. Oops. All right, so we're not done yet, but I'll stop right there. Any questions on how that works? Yeah.
I know that sometimes like they have a certain shape.
Yeah, we'll get to geometry later. Okay, but does that make sense how to set this up, how to draw it? Okay, now remember, chemists are very what? Lazy. We don't want to draw all these dang dots, dude. And so instead of drawing these dots and these circles, what we do instead is every time 2 electrons are shared, we just draw 1 line in between them. Okay. So every time you see 2 electrons that get shared, you're just going to draw a line in between them. Okay. And this is called a single bond. So here, every time you have 1 line, it's called a single bond. Okay. And 1 line represents 2 shared electrons. Okay. This will be very important as we go later, because if there's a single bond, there's a married bond. I'm just kidding. Double bond, triple bond. Yeah, so there's different types of bonds. Okay. So that's how you draw the Lewis structure of an element. I'm sure you've seen pictures of this like on a TV show or movie, or maybe on a science textbook or something like that, where you have structures of these molecules. But yeah, that's how you draw them. All right, one last thing that we need to do, because we need to answer all parts of the question. We want to identify the bonding and lone pair. Now, bonding electrons are pretty simple. It's the ones that are involved in the bonding, in the sharing. So how many total electrons are being shared right now? Yes, 6 total electrons are being shared, and the bonding electrons are here in the lines. These are the bonding electrons. And the lone pair electrons are the ones that exist in pairs, but they are not being bonded. So how many lone pair electrons are inside of this fluorine? Yeah, there's 6, 6 here, 6 here. And how many lone pairs does nitrogen have? 2. There you go. So I'm not going to write that down there, but bonding are the ones that are in the bonds. Every single line is 2 electrons. And then the lone pairs are the ones that are not being bonded. Alrighty, we'll do 9.7, and then actually we could probably move on after that again, but let's try 9.7. But before you guys do that, I do want to give one more rule that'll help you guys out here, where you're going to be drawing CH4. And the other rule is that I'm going to add on to the first one. It's not only the more electronegative ones, so the more electronegative ones and hydrogen go on the outside. Now, hydrogen always goes on the outside. And that's because hydrogen can only have 2 electrons in the first shell. So it's too small to go in the middle because it can't connect with more than 1. And so just keep that in mind, okay? I want you guys to draw the structure of CH4, and then again, identify the bonding and lone pair electrons. Take about 2 minutes to do that. You check with the person next to you. and then we'll go over it together. All right, I'll give you maybe 30 more seconds to finish up, and then we'll go over CH4. Can you throw it? Yes. All right, you guys ready to go? Kind of. Okay, so let's go over CH4 and then we'll move on to some more practice problems. So for CH4, we have carbon. And so how many valence electrons does carbon have? 4. So we're going to do C, 1, 2, 3, 4. And then how many does hydrogen have? 1. And then there's 4 of them. So we can just remember hydrogens always go on the outside. And you can kind of see already how it's going to form, right? Okay. So hydrogen needs how many more electrons? 1. So hydrogen needs 1 more because remember, the first shell can only hold 2. No, you're good. And then carbon is like Molly told us, carbon needs 4 more, right? Because carbon has 4, it wants to get to 8. And so what's going to happen is carbon is going to share an electron with this hydrogen. This hydrogen is good. This hydrogen, that one's good. This one is good. That one is good as well. So this is what CH4 is going to look like. And it's because carbon now has an octet. Hydrogen is an exception to the octet rule, obviously, because it can only have 2. And so how many bonding electrons are there in this molecule? 8, yeah, 2, 4, 6, 8. And then are there any lone pairs? No, so there are 0 lone pairs. Okay, so that is how you draw these structures using the Lewis structures.
Yes.
No, they're sharing electrons.
There you go.
You could have made a joke there. I was trying to like set up a joke.
I could have, but I don't need the assist. I can't let you rack up your assist numbers. I'm trying to be the GOAT here, okay? All right, let's do some more practice problems. So we're gonna draw the structure of these three compounds. Now I'm gonna give you guys, I'll give you 2 minutes to do N2, and then I'm going to go over it, but if at any point you're comfortable doing these on your own, you can just kind of ignore me and do more than just N2. But I'm gonna start off just by having you guys do N2, and then we're gonna finish off with CO2, NH4+, and then we'll take our break afterwards. Take 2 minutes. You can work with the person next to you again. Draw the structure for N2, CO2, and NH4. Actually, sorry, not N2, O2. My bad. O2. That's all about me.
O2.
Yeah,
Is there
O2.
another O?
Yeah, my wife, she's the other O. And then we make O2.
There's O1 and O2.
But I'm unstable without her. That's what I call it chemistry. Yeah.
Is that how you got married? Is the pickup line?
Is that how I what?
Got married. Is the pickup line?
So how? She doesn't understand chemistry.
Oh.
She said she told me she took honors and then she doesn't remember anything, which I'm pretty sure is what's gonna happen to you guys too.
We're never going to remember this class, but all we're going to remember is something on our
You're just gonna remember my fart jokes. 30 years from now, you're gonna be telling your kids, you know, I had an AP Chem teacher that literally just talked about fart.
If we're gonna remember this on our record, they're gonna be like, "Oh no, one of your classes is like a C or something," and I'm like, "Which class?" C chemistry. And then I just remember the fact that you have to work.
Well, I'll just be honest with you. Once you graduate high school, nobody talks about your high school grades anymore. Nobody cares about your high school GPA, what you did. When you get into college, nobody cares what college you go to, except your parents. No, like for real. I have friends that like they're managers now and they're hiring and they tell people don't look at their school or their GPA. We don't care. Yeah, absolutely. I mean, you do need to be smart and have certain skills, but the school you go to is not I think, the best reflection of that. I mean, unless you go to like some very specific program like Caltech or MIT or something like that. But even then, it's like they'd rather have someone who has more job experience and work skills. That's what you think. That's a lot. Yeah.
Well, you gotta add these certain things on here, activities, right? And then I looked at it. I had
Yeah. I tell everybody, just go to community college, transfer after 2 years. For you guys, that's why that Long Beach Promise thing is such a good deal.
My parents don't want me to go.
Why not?
Because they just want me to get into somewhere good.
Save money though. Save a lot of money.
I think it's also because their dad works at LBCC or something. They could go there.
You go to a different community college.
I don't know, like, from what I hear, Compton's really bad.
Well, I'm not saying go to Compton then.
Compton.
There are other options other than LBCC and Compton.
Cerritos.
Cerritos has a pretty high transfer rate out. Yeah. Oh, it depends.
I don't know. I just want to make music, so I just want to produce. I don't know why I would need to like learn the basic stuff in my life. It's not normal. I mean, obviously, it's good to have a backup. But
I mean, it's also good. I think one of the best or one of the only good things about taking all these classes in high school is you have learn to do stuff you don't want to do, because that's life. Like, you have to do so much stuff you don't want to do. And so many people like fall behind or get stuck because they don't know how to do that. Well, I mean, if you do, I don't know you. All right, so if you guys are still working on the other ones, feel free, but I'm gonna start going over O2. Okay, so O2, how many valence electrons does oxygen have? 6. So we have 1, 2, 3, 4, 5, 6, and then there's 2 of them, right? So I'm gonna have to draw another one next to it. Now there's no middle for O2 because there's only two elements. So I'm just gonna put them next to each other. But if you put it like top and bottom, that's fine as well. So if we take a look at oxygen, how many more electrons does oxygen need? Yeah, they both need 2 more. Okay, so what's gonna happen is this oxygen is gonna share an electron with this oxygen. Now, if they're sharing 2 electrons, do they have an octet now? No, because there's 1, 2, 3, 4, 5, 6, and then there's 7, which means they're gonna have to share 1 more pair of electrons, and that's how we'll get the 8. And so if we wanted to redraw this, just to make it a little bit neater, it would have each oxygen would have 4 non-bonding electrons, and there would be 2 lines in between them. And this is what we call a double bond. Okay, it forms a double bond so that it can share 4 electrons, 4 shared electrons. Okay, remember, because every line represents 2, right? And so they need to share 4 electrons with one another for both of them to get the octet. So I vaguely hinted at that earlier with the double bond thing, but if you guys didn't get that, that's all good. Okay. Yeah, this one, it makes it look like a face here. Or this one too. Yeah. Yeah, like on a molecular level, no, we can't. Yes and no. We can't. So the way that we see things, right? Dang, dude, you're having me go on 10. So let's say this is your eye, okay? This is your eyeball, okay? This is your retina. Okay, and then this is my eye. Okay. This is your eye, this is my eye. Y'all messed up. You guys are laughing. Okay, anyway, so this is your eye, and then how do you see things, right? It's light, right? Like let's say that this is me, Mr. O. Okay, light from hits me, and then it bounces off and it goes into your retina, and then it goes to the back of your eye, and then that's how you process it. Basically, you need light, right? The problem is when you get molecules this small, they don't reflect light the same way that macroscopic stuff like us do. And so you can't really see it. So what we do is we get like these electron lasers, and we shoot a bunch of electrons at it. And that's one way for us to see it, but you're not really seeing it in the traditional sense, right? We also use radiation, like magnetic resonance, to see light, because every single one of these has a different electrical property, right? And depending on how they're connected with other ones, we can use that to create graphs that show like peaks in electrical energy. And that's one way we can see it, but no, we can't see it in the traditional sense. Even though I can squint really hard, you can't see it. It's too small. Anyway, so that's O2. Okay, let's do CO2 now. Okay, so we already talked about oxygen. It has 6. Carbon we know has 4, right? Now, which one of these is more electronegative, carbon or oxygen? Yeah, oxygen. So it goes on the outside. So we're gonna put oxygen on the outside, put carbon on the inside, oxygen on the outside. Okay. We know that oxygen has 6. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and then carbon has 4. 1, 2, 3, 4. Okay. We said oxygen needs 2 more, and we said earlier carbon needs 4 more. Okay. So I think some of you guys might be able to see the pattern already. So this oxygen needs 2 more, so it's gonna bond with this carbon right here. And since it needs 2, it's going to bond 2 times. Okay, this carbon still, now this one needs no more, and this one also needs 2 more. So we're gonna bond 2 times. And then if we do that, all of the molecules now, or all the atoms have an octet now. Okay, because this oxygen has 8, it's 4 lone pairs, 4 bonding, 4 lone pairs, 4 bonding, and then carbon has 4 bonding. And so CO2 would look like this. So there are 2 double bonds.
There's a question about the geometry about it.
Uh-huh.
Is the reason why like the electrons like go towards the outside because like the electrons they have the same charge like pushing each other?
Yeah, they repel one another. We'll get to geometry later. Yeah, don't worry too much. Just get comfortable drawing these and understanding what they look like. Any questions on CO2? Yeah.
When there's more
Hydrogen goes on the outside and higher electronegativity goes on the outside. Oh, not necessarily. Yeah, not necessarily. For these smaller ones, yes. And that's why they form these, is because the more electronegative ones like to take it from the less electronegative ones, but not necessarily. Yeah. Good observation though. All right, you guys think you could try NH4 plus on your own? Yeah, I'll give you guys 2 minutes to do that. And then after that, we'll take our break. NH4 plus. All right, 30 more seconds, guys, and then we'll go over it. No, I don't invest. Well, I have changed my investing strategy recently.
Or did they attack the army using acid?
Why?
Neutralizing space. I feel like it's told this one. Sick cat.
You bury him.
We give you some more chemistry.
Isn't it a dead chemist?
No, this one's a sick chemist. Like I said, it's like if you can't heal you, can't cure it, then you might as well bury it. Oxygen, nitrogen, sulfur, sodium, and phosphorus walking through a bar. Oh snap! That's the bar.
All right, you guys ready to go? I seem so tired today.
Are all these jokes too basic for you? Because I see no reaction.
I've heard all. Okay, so we have NH4. Now, for this one, there's a weird thing going on because there's a positive sign, right? And so if there's a positive sign, what does that mean? Is there,
Electron missing.
yeah, there's one missing electron. So there's one less electron inside of this whole thing, right? So what we can do is we can actually speed up the process. We don't have to draw all the individual electrons. So let's count how many total electrons will be in this molecule, okay? So how many electrons, valence electrons, does nitrogen usually have? 5. Yeah, dude, English, man. I failed Spanish, I told you. Okay, so how many does hydrogen have? 1. But there's 4 of them, so that means it's gonna be 4. Okay, everyone following along with me so far? So 5 from nitrogen, 4 from hydrogens. But then since there's a positive sign, we have to subtract 1. So how many total electrons will be inside of this molecule? 8. Okay, so 8 total. And so what we can do, and this will actually help once we get to bigger and bigger molecules, is we can rearrange the atom, or we can arrange the elements without drawing the electron. So we know that nitrogen is going to go in the middle because hydrogen always goes on the outside, right? So we can actually just put them in their positions without drawing all of the electrons. Now, if you guys might have done it that way, but that's totally fine. That's a great way to do this problem. But once we get to bigger molecules, this method is probably going to be a bit easier. Now, the rule still applies. We still want to make an octet for everybody, 2 for hydrogen. Okay, so what we're going to do is there needs to be a connection between every single one of the elements, right? Because it's still one molecule. So we're going to draw lines with all of them. And then we're going to see how many electrons we have left over, if we have any, and whether or not they form an octet. So there's a connection here, and then hydrogen is happy, and then all the hydrogens are happy. Does the nitrogen have an octet? Yes, nitrogen has an octet because there's 2, 4, 6, 8. And then we hit the number of electrons that we need, which is 8. And so this is going to be our structure. Now, if there is a charge, we want to put it in brackets and put a plus on the outside. That's it. So this method is really easy because we just need to arrange them. We don't need to draw all the electrons. We just draw the lines, and then we're good to go. Yeah.
Will the missing electron ever affect like the way it bond? Like if there's an electron missing, it would be missing from like nitrogen or hydrogen.
Huh?
Like, okay. Because like if the hydrogen is missing the electron, which gives you the positive, right? Would that make a difference if it was like nitrogen instead for like bigger compound?
Oh, no, not really. Just use the same method. Just do the counting. Just count that. Do the accounting first, like this, and then it'll help you set it up for bigger ones. Sorry, I didn't understand the question. All right, we'll take a quick break. So if you need to go to the restroom, go to the restroom, and then we'll come back, and then we'll do a little bit more, and then we'll be done.
It's why we like when rappers break up with people. They just like spit
Oh,
out.
for sure, dude. All that pain and emotions comes out in a fire album. Okay, guys. So we already looked at this, but just to kind of review and kind of have it in one place to summarize. Single bonds, they're formed when atoms share 2 electrons with one another, right? We already know about that. It's represented by one line. And so we have an example here with H2O, water. It has 2 single bonds. Double bonds are when they share 4 electrons, 2 lines. So CO2, we just did this example. And then you can even have a triple bond where they share 6 electrons with one another. And that is represented by 3 lines. So we have N2, which can be represented like this. Okay, and everyone asks me this every year, but there is no quadruple bond. Anyone want to take a shot at why there is no quadruple bond? What was that? Yeah, so you would need 8 electrons, but they're still sharing them, so they would form the octet. So theoretically, right, if we had 2 carbons, right, carbon has 4 each. So if we had a quadruple bond like this, there would be 8 until they form an octet. But why would there be no such thing as a quadruple?
Like hypothetically, or just like hypothetically works right there, right? But like,
yeah,
we're talking about the real world.
in real world.
So much other stuff that will bond for it. So it's
So it's not because there's so much stuff that'll bond before, but what do electrons do to one another? Yeah, they repel. So if we have 8 kind of between two of them, it's not stable anymore, right? There's too much repulsion. And so the best we can get is actually 3. And so this, in reality, there is N2. It's the most common gas around us. And so there's 6 electrons shared between 2 nitrogen atoms, but we can't have a quadruple because the repulsion would not allow 8 electrons to be shared between 2 electrons, okay? So just a little fun fact, there's no quadruple bonds. Yeah, science. All right, so one key thing, and this is the last thing we'll finish off with today. The type of bond between 2 atoms affects the distance between the atoms, right? So depending on whether there's a single, double, and triple bond, it's going to affect the distance between the 2 atoms. And generally, the length of the bond between 2 atoms decreases as the number of shared electron pairs increases. What that means is that single bonds are going to have the longest distance between the 2 atoms, okay? So the triple bonds will have the shortest distance, which makes sense because if there's a triple bond, it's held a lot tighter together, right? And then the longest bond length is going to come in the single bond, okay? That's basically what this little blurb here means, okay? Single bonds are the longest, doubles are in the middle, and then triple bonds are the shortest type of bonds. That's when they're closest. The 2 bonding atoms are closest to one another. Huh? Yeah. Oh, was there a question about this?
Let's just say I need to provide something.
That's all good. And that's why we learn, right? I'm glad I still have a function in your life. Okay, so we're going to do one last problem to finish up for today. 9.8. So if you take a look at the CO bond, and you don't need to draw this, but the CO bond in carbon monoxide is 1.13 angstrom. Angstrom is just a way of we measure things like meters. It's just a small type of measurement. Okay, while the CO bond in CO2 is 1.24 angstrom. Okay. So without drawing a Lewis structure, do you think CO contains a single, double, or triple bond? Okay, so just take a second to read that and think about this. I actually pulled this from the AP test and I made it into a work, not a multiple choice. But just take a look at it. What do you guys think? Okay, so let's take a vote. Who thinks it's a single bond? Carbon monoxide, CO, has a single bond. Who thinks it's a double bond? Who thinks it's a triple bond? Okay, well, it's not a triple. Okay, so let's go over this. Okay, so the options are single and double. So basically what they're saying is that carbon monoxide, the chemical formula is CO. Okay, and then we have CO2. Okay, now this problem is saying that in the connection, the bond between carbon monoxide, the distance is 1.13 angstroms. Okay, and then for CO2, it's 1.24 angstroms. Okay, so we looked at CO2 earlier. What kind of bond is between CO2? Yeah, double. Okay, so this is a double. Okay, now, so that means that this double bond, the CO double bond, or this, yeah, the CO double bond has a distance of 1.24 angstrom. Now, if you go from 1.24 to 1.13, is the distance getting bigger or smaller? Smaller. Okay, what bond is smaller, shorter than a double bond? Triple. Did I just say that it's not a triple? Yeah, it's a triple. Sorry.
Oh.
Sorry, guys. I'm still getting better. Okay, so this is a triple bond. And the reason why is because In CO2, it's a double bond. Okay, we know it's a double bond. We just did the drawing for it. But just by looking at the structure and counting the electrons, we know that it has to be a double bond. This is shorter than the CO2 bond. And so that means it has to be a triple bond. And if we actually draw the structure for carbon monoxide, you'll see that it looks like this. Okay, so it's a triple bond. All right, so we did a lot of stuff today. We covered a lot of material, so thanks for sticking through it, guys. Again, reminder that the homework is going to be at the end of the semester, day of the final, so you do have some time. Oh, shoot. But yeah, enjoy your lunch. Have a great weekend. I'll see you guys later, guys.